Hello everyone, welcome back to the Electrical Circuits and Network. Today we are going to discuss Kirchoff's Voltage Law, which is popularly known as KVL. In the previous sessions, we have discussed the Kirchoff's current law, that is KCL, and nodal analysis based on that. We have also solved a few examples based on this nodal analysis. Okay. In this session, we are going to use this KVL to solve a given circuit to find unknown voltages and current. Okay, so let's get started. Before going to actual KVL law, we will discuss some basics related to that. The mesh and loop. What is meant by mesh and what is meant by loop? The loop is a set of branches forming a closed path. The set of branches which forms a closed path is known as loop. Mesh also, it is a set of branches forming a closed path, but it does not contain any other closed path in it. That means it is the smallest possible closed path formed by a set of branches is known as mesh, and loop is any set of branches forming a closed path is known as loop. Okay. See here, this is the network where from this V1 through this R1, R3 and R7, this one path is available. Okay, this is also one closed path starting from this R7 again back to R7. And starting from this R3, R2, R4 again back to this R3 is 3, and from here it's this starting from this V1, then through R1, R3, R4, R5, back to this V1 is the fourth closed path. Okay. These all are first, second, third and fourth, all are the what loops we have in this given network. Okay. So observe here, this loop number 1, loop number 3 and loop number 2 are the smallest possible closed path available in the network, whereas this loop number 4 contains this loop number 1 and loop number 2. That means loop number 4 contains loop number 1 and loop number 2. Okay, so this one loop number 1, 2 and 4 will be mesh, this 1, this 2 and this will be 3 are the mesh, but this 4 will be only loop. Okay, because it is a closed path formed by a set of branches, but it contains other loops also. Okay, so remember this is the difference between mesh and loop. So then sign convention. Suppose if we are using this KVL law, then this sign convention and this potential rise and the concept of potential drop is very important. Suppose this is the given circuit. In that circuit we assume the current direction as this direction. Suppose we are assuming that the current direction is as this one. Okay, then we know that the current always flows from higher potential to lower potential. That means this will be the plus and this will be the minus. This is the sign convention we use. Suppose the current flowing through the resistor is in this way, then again currents flow from higher potential to lower potential. So higher potential will be denoted by this positive sign and this will be the negative sign. This is the sign convention for resistor used in a network when we are applying the KVL law. Then again potential rise. Suppose this is the battery. Okay, this is the battery. This is also same battery. This is the negative terminal and this is positive, this is also negative and this is positive terminal. Now, suppose if we trace the path along a closed loop from negative to positive, negative end of the battery to the positive end of the battery. That means if our direction of a current is, assumed direction of current is this, then we are tracing the path from negative to positive. Okay, negative to positive. That means change from negative to positive. That means it will be potential rise. Okay, it is taken as potential rise. Suppose if we trace the path along a closed path from positive to negative. Suppose we have the current path assumed as in this direction. Okay, so we are tracing from positive to negative. That means voltage is drop. So here we have taken it as a voltage drop. Okay, so suppose this is V volt. Then if we are tracing from negative to positive, we will write positive V because it is potential rise case. And if we are tracing from positive to negative, we will write negative V because it is a potential drop. Okay, in this manner we are going to use the sign convention and this concept of potential rise and potential drop. Then let's see what is the statement of Kirchoff voltage law. The Kirchoffs voltage law, which is known as KVL, it states that it is the algebraic sum of voltage around a closed loop in a circuit must be equal to 0. The algebraic sum of voltage around a closed loop in a circuit must be equal to 0. When we are applying this KVL to a closed path, the algebraic sum of voltages around that closed loop in a circuit must be equal to 0. That means summation of voltages across element of that loop equals to 0. Or we can write it as a summation of voltage rises equals to summation of voltage drop around a closed loop taken. Okay, this is the statement of voltage law. Let's solve numerical based on this law. This is same as KCL only, but in case of KCL there will be algebraic sum of current meeting at node equals to 0, and in this case it is the sum of voltages around a closed loop equals to 0. This is the question given where this 2 ohm, this 5 volt battery, then again 3 ohm and this 15 volt are connected in this manner, and we want here value of current I. Okay, for that current I, here 2 batteries are there, so we cannot write directly as I equals to V, total voltage V upon total R. So first we have to write the KVL equation, and the assumed direction or the direction given was in this manner, that is clockwise manner. Okay, so first we will write the equation by applying the KVL. Okay, so for that first we will write as the current direction is in this manner. Okay, current direction is from this to this, that means current is flowing from here side, so this will be the positive, this will be negative. Okay, again battery have this positive and negative, this will be positive, this will be negative, again this is minus and this is positive. This is the battery voltage. Okay, so we will write first as we are starting from here. Okay, we are starting from here, suppose. So this will be plus minus voltage drop across 2 ohm. So plus minus, we are tracing from plus to minus, so minus V 2 ohm, that means voltage across 2 ohm. Okay, so we come here, then positive, negative, positive to negative. So negative voltage drop, voltage is what? 5 volt. then again plus minus, then minus voltage across 3 ohm, then again from here negative to positive, so positive 15 volt equals to 0. Okay, this is by applying KVL to the given loop. Here only one loop is there, so we have only one equation. So what is voltage across 2 ohm? Is the current flowing through 2 ohm is I, so I into this 2 ohm, 2I into 2, that means 2I. And voltage across 3 ohm is current into resistance, so current into resistor I into 3, so it will be 3I volt. Okay. Now putting these values in this equation 1, we have this minus 2I, this value minus 2I, so this minus 5 and plus 15 is what? Plus 10, and this minus 3, so voltage across 3 ohm is 3I, so 3I equals to 0. Okay, so this will be 10 equals to 5I, so I will be 10 divided by 5 equals to 2 ampere. This is the required value of current. Okay, in this manner, with the help of KVL, we can find the unknown current when there are a number of voltage sources and number of resistance connected in this manner. Okay, let's do another example. Here the question is, the circuit is given, and here also we are going to find the value of I, the current flowing through the circuit. The direction is given. Okay, if not given, then assume any direction, either clockwise or anti-clockwise. We prefer clockwise direction. Okay, so first we will do the sign convention. Okay, this is negative, positive, this is negative, this is positive, this is positive and negative. Okay, for the resistances, as the current is in the clockwise direction, that means current flowing through this 2 ohm will be in this direction, so this will be the plus and this will be the minus terminal. So again current is in this direction, so this will be the plus, this will be the minus. Current is in this direction. Okay, so this will be the plus, this will be the minus. First we will do that sign convention, and then we are going to apply the KVL. Apply KVL to loop given. Okay, so we are going to write the KVL equation. Let's start from here at this point and come back to here only. So negative to positive, so potential rise, so for potential rise plus 10, then here positive to negative drop, so voltage across 2 ohm, and from here negative to positive rise, so plus 10, here negative to positive to negative minus V, voltage across 1 ohm, positive to negative voltage drop, so minus 5, so positive to negative, so minus voltage across 1 ohm, voltage across 1 ohm. Okay, then again come back to this position equals to 0, because we know that algebraic sum of voltages around a closed loop equals to 0. Okay, so the voltage across 2 ohm is what? Current I into resistor. So V2 ohm will be 2I, this V1 ohm will be 1 into I, that is I. Now so this voltage across 1 ohm will be what? 1 into I equals to I. So putting these values in this equation, so plus 10 minus 2I plus 10 minus I minus 5 minus I equals to 0. So this will be the 10 plus 10 minus 5 will be 15, and this 2i minus I minus I. So this 2, 3 and 4, 4i. So 15i equals to 4i. So I will be 15 divided by 4, okay, which is nothing but 3.75 ampere, and this is the required value of current. Okay, this is 3i equals to 3.75 ampere. Now this is the circuit is given where 2 ohm, 2 ohm and this 1 ohm are connected with these two voltage sources. We have given this direction of current I, and we want this value of I. Okay, this is your today's task. Solve this and let me know the answer in the comment section. Okay, we will solve this task in the next session. Okay, and also in the next session we are going to discuss the mesh analysis, which is based on which is the technique based on this KVL law, Kirchoffs Voltage Law. Okay, so till then stay tuned and keep learning. Thank you.